theme of my report is on possibility of unloading control at leg orthotics. Is it loud enough? I apologize for my pure English, so I will be partly speak and partly read. Here's the content of my report. I'll pass it on and proceed to the content. So, the appearance of new materials in the last 30 years led to gradual substitution of simple tools such as plaster casts and splints by a new type of orthopedic devices, high-tech orthoses. The latter provide means for tightening and flexible adjustment of the orthosis for a particular patient throughout the treatment period that allows providing better fixation and unloading of the problem area, reducing the time and improving the quality of treatment. Orthosis, from Greek straight, right, is a special technical device used for fixing, unloading, correction and activation of the injured limb function. In a broad sense, it includes the entire range of orthopedic devices, from knee pads and insoles to corsets, splints, apparatus, and so on. We dealt mostly with tutors, a subtype of orthosis consisting of sleeves, sometimes with a shock, interconnected by buses without joints, with fixing, Velcro, straps, metal brackets. The main advantage of an orthosis is possibility of its tightening, adjustment for a particular patient. That is personalization. Here are some photos of tutors. Basic functions of orthosis are fixing and unloading of the problem zone. The cause of unloading is as follows. Extending one's lower limb length tends to reduce under the action of the body weight. An orthosis which is tightly fitted to the limb prevents it and undertakes part of the body weight. Full loading a limb before consolidation can lead to complications and damage to the problem area, while underloading results in marked weakening and atrophy of the musculoskeletal system and recovery time elongation. Therefore, obviously, there is some optimal level, more precisely a program of unloading, in which on the one hand reduces danger of repeated injuries, and on the other hand, it is possible to carry out dynamic correction of the damaged segment in functionally correct position. The latter promotes restoring the limb locomotor function and early rehabilitation in the best possible conditions under different location and nature of lesions. This determines the importance and urgency of the problem of studying mechanisms of unloading and ways to manage it. So the rate of regeneration depends on the loading level and program. In view of the main advantage of orthosis, possibility of tightening, a natural idea is to control unloading through the change of lateral compression or tightness. Here's the picture illustrating the basic idea of the work. To study experimentally the problem of control of unloading in orthosis, we took two types of orthosis, you see them here, and used the system DEFORMABILITY. DEFORMABILITY system is used for measuring of pressure of plantar on the support. It's hardware and software suite using special tensometric insole insoles inserted in parallel right beneath both feet. For the right, into the orthoses, and for the left foot, right into the shoe. The athlete suit includes a set of tensometric insoles of different sizes, with just about 200 strained gauges on each insole, the signals from which allow to obtain, remember, and display on the computer pressure distribution patterns under each foot, integrated photos, and so on. So here, here you see the athlete sensors on the orthoses, which give the signal of distribution of underplantar pressures. The interface of the athlete is as follows. In the upper left window, we see trajectory of center of pressures. To the right is the topography of underplantar pressures. And beneath is the charts of integrated loads on each foot. Green on the left foot and red on the right foot. We dealt mostly with charts of integrated loads. Here we see some typical graphs of it, and coefficient of unloading in orthosis was determined as ratio of the maximum load on the feet without an orthosis to the maximum load on the feet with an orthosis. At the right side, you see typical values of coefficient of unloading. Here it's something about 1.3. So we have some preliminary graph of dependence of coefficient of unloading from tightness, and it was seen that high scattering, it has high scattering, partly before limited accuracy of suit athlete, and partly of the deficiencies of methodic, used methodic. So we are taking special measures to standardize experimental conditions and control parameters. Here's the list of those measures. Among them, standard cotton stocking, standard positions, and so on and so forth. After this, the measurements were repeated and tightening was digitized. So we have such dependencies of coefficient of unloading on tightening for walking and standing. In any case, the variability of CU on tightening wasn't valid enough, and in any case, we don't see that CU becomes higher with tightening becoming higher. To understand the experimental results obtained, we developed several biomechanical models. Main tissues, main materials and tissues we deal with are cartilage disc, tubular bone, footer, local supports, muscle tissue, and orthosis sleeve. On the left is some schematic, scheme, and evaluation of stiffnesses of each of these components and comparison of them made it possible to produce the biomechanical model of loading the leg, of loading a leg in orthosis, which is given in the right. P is the body weight. This is the tubular bone. This is the orthosis itself, and this is muscle tissue. That is local supports. Formalizing of this model and calculating the coefficient of unloading gave the result given below. PF is the part of weight falling on foot, and K is quite the coefficient of unloading. Assessments give for K the results. The results 1.6 till 2.1. That model didn't took into consideration. That model didn't catch the dependence of unloading on tightness. So to take it into consideration, the model was revised. I won't. Well, integration. Here some interim findings are listed. I will not stand on it. And the main point is that in reality there are dry friction conditions, and we might take it into consideration. So further, some models were propelled to take into considerations friction between the leg and the orthosis. Here below is the condition, the threshold condition that gives us that friction coefficient must be less or about 0.25 in order to be sleeping. Coefficients of friction were measured experimentally for standard cotton stocking and slippery stocking. And we see that for standard cotton stocking there are no slippery. And so there are no dependence of coefficient of unloading on tightening. For slippery stockings, polyacryl, there is. In the next two models, allowance for deformability of shin was taken. Firstly, there was considered conical model by the method of boundary integral equations, and it gives the same results as an experiment. And then it was the same was done with the technology of computer tomography scan, data preparation, and fab package. Here are computer scans. This is converting CT images into a film-green model, and here is the resulting final element mesh and the results of calculating of areas of adhesion on the contact on skin orthosis boundary. We see that at K equal to, at friction coefficient equal to 0.4, there is adhesion, and at K equals to 0.1, no adhesion areas there are, and it's ideal sleeping. And at last, experiment was done with slippery stockings to try the results, the theoretical results obtained. We see that in walking we obtained no dependence of coefficient of unloading on tightening, but standing at the initial branch of the curve, we see pronounced growth of the curve, and then stabilization of it, and some results. We need further investigation of solid models, taking into account the effects of friction and non-classicality, anisotropy, etc., to refine the conditions of unloading coefficient growth with an increase of circumferential tightness. Model piston effects, considerations of modified unloading control variants, creation of control gaps, tabs, shock absorbers, etc. Improvement of the experimental procedures, experimental verification of computation of theoretical conclusions based on selection of suitable materials and loading conditions. Construction of two-model sample of active semi-automatic orthoses, which is being done now. Development explorations of options elastometry, elastography to measure mechanical properties in orthoses, and some other and some other.
Okay, thank you, Ilya. And I think we